You secure your login pages, you sanitize your inputs, and you have WAF in front of your application, you feel safe. But what if I told you there is a vulnerability that operates beneath all that? A vulnerability that tricks your server into seeing a single request as two. An attack that can poison caches, hijack user sessions, and bypass security controls entirely. This is called HTTP request smuggling. So bear with me, I'll explain what HTTP request smuggling is and how common this vulnerability you can find in many websites. HTTP request smuggling is a technique which interferes with the website process sequence of HTTP requests that are received from one or more users. Request smuggling are often critical in nature, allowing to attacker bypass security controls, gain unauthorized access to sensitive data. Let's say here you can see that the vulnerable website is sending some malicious data in the form of the red highlighted syntax, right? Gain unauthorized access to sensitive information and directly compromise other applications. Like here you can see that the backend processing two requests. Actually the front end is saying that it's actually a single request. So here comes the discrepancy. Request smuggling is primarily associated with HTTP 1 requests. It is built in with HTTP 1.1, right? HTTP 1.0 and later was not that much affected about this vulnerability. However, websites that support HTTP 2 may be vulnerable depending on their backend or architecture. It can be possible that the website those are using HTTP 2 are vulnerable. There are researches, but we'll explain these researches upcoming videos. So you might be thinking how common request smuggling is. I don't get it, right? So the thing is, today's web application frequently employs chains of HTTP servers between users and ultimate application logic. Let's say you can see here is a front-end server and the back-end server exists. Means there are two servers behind the single request and response model, right? Users send requests to a front-end server, sometimes called a load balancer, which is this one, like Akamai, like Cloudflare, and bunch of other load balancer like AWS, Google Cloud, and many more. They are also called reverse proxies, and this server forwards the request to one or more backend. This type of architecture is increasingly common, and in some cases it is unavoidable in modern cloud-based applications like Google Cloud and bunch of AWS services. They are all using the same architecture, front-end and back-end architecture, as you might see. The problem arises when front-end server forwards HTTP request. Like here you can see these are the HTTP requests going from two different users. And the backend server, it typically sends several requests over the same backend network connection. Problem arises when the connection is same. Like these two requests are going, these are the chunk of the request stream of the bytes. But what happened actually in the backend is processing a single TCP connection requests in a pool, and which can be a socket. Maybe it is called actually a socket, and it usually gets poisoned in HTTP request smuggling. So what happened after that? The backend request receives these requests. Because this is much more efficient and performant, the protocol is very simple. HTTP requests are sent one after another, and the receiving server has to determine where one request ends and the next start, right? There is a mechanism which tells the backend server which one I will consider, which one request is from which user. How do I distinguish these two requests? Or there can be bunch of requests, like thousands of requests in a connection pool. So how do I differentiate this request start from there and end from here? There are two content type headers which is normally being used in order to identify these differences from the requests from the front end and the back end requests, right? So the ambiguity caused by these headers, like content type header and the the transfer encoding header. In situation, it is crucial that the front-end and back-end systems agree both the boundaries between requests. Otherwise, the attacker might be able to send an ambiguous request that gets interpreted differently by the front-end and the back-end server. This causes the problem. Here you can see that the front-end and back-end server has an ambiguity. Why it's that? Because the attacker has used a malicious request where it confuses passes the front end that it's a normal request, all is well, right? But in the back end request, the back end process it's differently, right? So this causes discrepancy. Don't worry, we will explore this in particularly more advanced. So here the attacker causes the part of the front end request to be interpreted by the back end server as the start of the next request. It is effectively prepended to next request and so can interfere with the way application process that request. This is a request smuggling and it can have serious impacts. You might be wondering that how these can be exploited. Generally speaking, it's really difficult to exploit these vulnerabilities, but it has a very serious impact if you can somehow manage to bypass, because it bypasses the front-end checks. Basically, Cloudflare, Akamai and bunch of other front ends can be bypassed easily with the HTTP request smuggling as of my thoughts, and you can do your research as well, but here I am going to show what I understand about this vulnerability. Most of HTTP request smuggling vulnerabilities arise because the HTTP 1 specification provides two different ways to specify headers, like transfer encoding header and the content type header. These are two different headers, so that causes the most ambiguity. Let's zoom in this request. What actually this request is. As you can see that the normal website.com is using content type header, content length header contains 11 bytes, right? That should be normal, like the front end server thinks that the content length header is 11 bytes and the backend server is also expecting the same as it is defined above. The body of the request causing the ambiguity here. You can see if the content length header is not 11 bytes, so that's the problematic situation we will see further. So transfer encoding header can be used to specify the message body uses chunked encoding. Especially we have discussed earlier for specifying a video, for sending a video on sending a video where are a large content like image, you may have to use content transfer encoding chunk. You are sending the data in chunk format, so that's why content type is not being used and transfer encoding may be used on the sending of the image data, right? So this means that the message body contains one or more chunks of the data. Each chunk consists of size in bytes expressed in hexadecimal, followed by a new line, followed by then chunk content. This message is terminated when the chunk size, and you can see that this message is terminated when the chunk size is 0. Like chunk size is, if it is 0, it is terminated at there, right?
The content length header is straightforward. It specifies the length of the message body in bytes. Here you can see the Q smuggling represents the body, and content length 11 tells this backend server and frontend server what's the length of the body in byte size, which is 11. So this is not very much problematic at that time, but it can be problematic when transfer encoding header is being used to specify the message body using chunked encoding. This means that the message body contains one or more chunks of data. Here you can see the transfer encoding is being used, and no, it's not explaining what is the actual length in numbers, but it is saying that it is chunked. First it maybe take this chunk and then this chunk and then this chunk. It can be the server front end or maybe the back end both takes these the request as in the form of chunk instead of the content length in byte size, right? So each chunk consists of the chunk size in bytes expressed in hexadecimal. Make sure you have to remember that these are expressed in hexadecimal, and also new line is being appended at the end of new chunk content, right? The message is terminated with the chunk of size 0. Here you clearly see that the message here, it tells the body of the request, right? What it's the researcher using the term message, which is the corresponding explanatory of the post request body. As HTTP 1.1 specification provides two different methods for specifying the length of HTTP message. Message mean body, right? It should not be confused with anything else. It is possible for a single message to use both methods at once, such that they conflict with each other. The specification attempts to provide this problem by stating that if both the content length and transfer encoding header are present, then the content length header should be ignored. This is the problematic. If content length header and the transfer encoding and content length both are present, then there is room for the ambiguity. Why? The funny thing is that why the specification scientists or engineers have made this difference, because there was an ambiguity, so they want to clear that ambiguity. There is no problem. This might be sufficient to avoid ambiguity. They made that specification change avoid ambiguity, and the funny part is it causes the ambiguity again when only a single server is in play. But nowadays we have seen the multi server structures, like infrastructure like front-end server and back-end server. So this is the problem, but not when two or more servers are chained together. In this situation, problems can arise. Two reasons here PortSwigger mostly referring that some servers do not support the transfer encoding header in request. Here the server means the backend server, which is the which can be a server like Apache, or Python server like Laravel, Python server like Django, and PHP server Laravel, and many other. Like here it is talking about the backend server. Some servers do support transfer encoding headers and some do not. Some servers that do support transfer encoding header can be induced not to process it if the header is obfuscated in some way. If the header is somehow misplaced, like here X is specified or anything, or double space are specified, some servers just ignore it and they did not encounter this transfer encoding header as a HTTP header. And the back, what they do, they truncate the white spaces and they truncate the other things and send it to the server. So this may causes the ambiguity. The backend server process it as a transfer encoding header, and the front-end server did not, process it as a transfer encoding header. This causes the ambiguity, which results if the front-end and the backend server behaves differently in relation to the possibly obfuscated transfer encoding header, then they might disagree about the boundaries between successive requests, leading to request smuggling. So this is the whole story of how request smuggling arise, how request smuggling became possible. So here is a single thing we have to admire, that websites that use mostly HTTP2 end-to-end are inherently immune to request smuggling. Here end-to-end means that the front-end server is also using the HTTP2 and the back-end server is also using the HTTP2. Then they are immune. If they are downgrading or rewriting the request from HTTP1 to HTTP2, the front-end server is doing, or the back-end server, then there is a problem. As HTTP2 specification introduces a single robust mechanism for specifying the length of a request, there is no way for an attacker to induce required ambiguity, because HTTP2 is different from the HTTP1. It's not hex based. It's it has a content window length, and we will explain it in further. However, many websites have HTTP2 speaking front-end server, but deploy this in front-end back-end infrastructure that only supports HTTP1. This means the front-end effectively has to translate the requests it receives from HTTP1. This again causing the translation or the rewriting, causing the HTTP2 request smuggling possible. So it's also called the downgrading process, which is resulting to the advanced request smuggling, which we will explain in further, right? Basically, HTTP request smuggling is performed when both content type and transfer encoding header is present in a request, and one is being obfuscated, like transfer encoding chunk header is being obfuscated from the front-end server, and the back-end server is processing it, and also the content length header is available. And specification says that if both headers, content length and transfer encoding, are present in a single request, so what we need to do, HTTP request, then the backend server should process the transfer encoding header instead of content length header, right? So there are four type of HTTP request smuggling: CL.TE, TECL, and CL.TE, TECL, and TET. Here you can see the front end server uses the content length header and the backend server uses transfer encoding, TECL. CL.TE done. CL mean front end server is using content length and transfer encoding is being used by the backend server. And what is the meaning of TE.CL? The front end server uses transfer encoding, the backend server uses content length header. As simple as that. TTB, the front end server and backend server both are using transfer encoding, but one of the server is ignoring one header, ignoring the transfer encoding, and the backend server mean it is obfuscated somehow or some way, in a way that it processes it differently, so it causes the TET possibility. There are other types, but these are not mentioned in this blog post, so we'll talk about these later. So here you can take a look. At the request which is causing the CL.TE, which is the classic or mostly famous or mostly known vulnerability type of HTTP request smuggling. So here the front end server uses content length header. You can see that the content length is 13, right? It is clear. So the backend server uses the transfer encoding. We can perform simply HTTP request smuggling attack. You can see backend server is processing transfer encoding instead of content length header. So this is problematic because this causes the ambiguity between the front end and the backend server. Backend server is configured in a way, or it did not support. So the front end server processes content length header and determines that the request body is 13 bytes, and it says that content length is specified 13 number, so it should be 13 bytes, no longer than that, up to the smuggled, right? This is the front end server saying that it should be like that, right? The request forwarded onto the backend server. The backend server process the transfer encoding header. What they do, they basically process transfer encoding header instead of any other, this one, right? The following bytes smuggled are left unprocessed. So what it is doing, the front end server is processing data until here. The rest of smuggled content, which is also the part of one request body, which is being unprocessed, and it can be appended to another request which is coming next to it, we have previously seen. So this was theory. I hope this makes things clear. We know to go and solve this lab and see how it's actually performed in real world attack scenario. In order to better understand this CL.TE vulnerability, which is causing the front end server the processing content length header and the backend server is processing transfer encoding chunk header. So in order, the front end server rejects other requests except get and post. It only accepts these both requests, and in order to follow this lab, the backend server should appear or should respond with gpost method. And here we also need to specify some to configure our burb in a way that it can exploit the HTTP request smuggling. So this is the final request, and I'm going to send, I just loaded the basic home page of my lab, and now I'm going to send 2 random requests to my pub suite. It should be super random, and one is attack request, right, and the second one is normal request. And I'm not going to waste any time. I just have to paste it here, the right solution, and I wanna make sure to explain it in a better way so that you can understand how it is going to be performed, right? So I have given this request. This request is basically containing the content length header and chunked encoding. The front-end server will process the content length header and the backend server is going to see the chunked encoding. So they are going to confuse. And the next request, which is the normal request, you can see when we send this normal request, we are going to see that the normal request is processing the G which is from the attacker request, and the normal request is being poisoned in that way. Hence it is poisoning the socket, and it can be devastating impact, right? Here I am going to specify just normal foo bar, and that's it. And I'm going to send this request again, see how it goes. But before you can exploit this, here you can see that this is HTTP2 request, and also the bulb suite, the recommendation is to not use HTTP2 because it is HTTP 1.1 vulnerability. That's why make sure to click on the inspector tab, and then here comes the request attribute. Just downgrade it into HTTP1, and you can see that the HTTP1 1.1 appears in the request. Do the same in this request as well, and make sure to downgrade this by the HTTP 1.1, and you will see that it is written at there. And the other setting, which is the update content length, the burp suite normally update the content length header, so make sure to uncheck it before going further, and in the second request do the same as well, and then send the request. And also one thing I have missed, that you should to own this new line characters in order to better understand it. So here I am going to send it. Here you can see it is saying that I have seen the gpost method, and it means that it has intercepted another some victim normal victim user request which we have sent bunch of time, which has been polluted with gpost. And you can, if you reload, you can see that he has solved the lab. So it means that what it does, it has poisoned the someone else request from the post to gpost, right? It was not his request, but it was someone else's request which is giving the response of gpost, and that's why it is causing the HTTP request smuggling. This was the basic explanation. We will go further in the upcoming sections.